Okay, so we are going to have a look at the law of conservation of energy, and the great thing about this is it revisits all the stuff that we did in year 12. So this is actually the same slide, I think, as that we used when we looked at this in year 12, but I've just said that it's expanded and I've added in a bit of information, okay? So we've got that the initial energy is equal to the final energy. We know that. That's something that's always going to be true. I know many of you do physics as well, so you've probably seen this idea a few more times as well. This is not a formula you should remember. Okay, this is just something I want to explain about like what happens in this particular system. So we know that the only thing I've added in is EPE for elastic potential energy. The energy, the elastic, the gravitational and the kinetic energy you have at the beginning will be equal to the elastic, the gravitational and the kinetic energy that you have at the end. However, if there is some kind of force, some kind of friction or resistance that is working against, that will be on the right-hand side, the work done against friction. If there is an engine or if there is a person who is putting some extra work into the system, that will be on the left-hand side. So the left-hand side has stuff that's going into the system. The right-hand side over here has stuff that is leaving the system, okay? So basically what we've got is the potential energy released or the energy going in is equal to the potential energy that is stored or the energy going out. I still think the best way of thinking about this is what I've written about in blue here. So I've written, consider the energy that it has at the beginning, and I tend to think of this as the energy it has in the bank, a bit like money. Like what energy does it actually have in its reserves? Some of this energy is spent in various ways. It is either spent and converted into another type of energy, or it is spent on having to overcome friction or resistance. Some energy is not spent, but is instead increased. E.g., the kinetic energy may increase if it gets faster because the gravitational potential energy is converted to kinetic energy. If there is a force or an engine doing work, then there is more energy in the bank to be converted. This is why it is on the left-hand side of the equation. So you should be trying to think about the energy that something has at the beginning. It's either going to stay in its current form, it's either going to get converted into another form, or it's going to get spent on overcoming friction. Those are the only things that can happen. And these questions are often quite large in terms of the number of marks that get awarded for these kinds of things. And it all comes down to the first line of the equation and taking your time with setting this up, okay? So we'll have a look at, I think we've got 4 examples. That'll probably take us to quite near the end of the lesson. And then when I see you guys on Friday, we'll just have a whole lesson of just practice, 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 okay? So here we go. A light elastic string, natural length 1.6 meters, modulus of elasticity 10, has one end fixed at point A on a smooth horizontal table. Smooth horizontal table means that there's not going to be any work done against friction here. A particle of mass 2 kilograms is attached to the other end of the string. The particle is held at the point A and projected horizontally along the table with speed 2 meters per second. Find how far it travels before first coming to instantaneous rest. Okay, so what does this, well, I'll start off. If we've got a table here and we've got a point A and we've got the point where it is in the string, the particle is actually at the point A, isn't it? Because it tells you that in the question. This is annoying how not straight that is there. So the string is just very loose at this point. Just ignoring all of this question and the mechanics of trying to describe it with mechanics, what would actually happen if you imagine this? There was like something attached to a stretchy piece of string and it was on a smooth table and it got pinged off in one direction. It's going to slide all the way along the table. The string is then going to stretch out until eventually it slows down because the tension in the string becomes great and it will ping it straight back. All we're interested in at the moment is that journey from it going all the way here to when it is stretched out fully and it is stationary at that point there. That's not, it's not compressed. It doesn't have any tension. I've got it just, that black line there is just like a loose string.
So what's making it move forward?
It says here that it is projected horizontally along the table with speed 2 meters per second. So it's saying some force, just some impulse made it move. Okay? We're not going to write that force on the diagram because because it's gone. That force was there, and it shot it off, and that force is gone now. It's been given the speed. So we need to think about what energy it has to begin with. Okay? That's the only thing it's got at the beginning. So it has... It is, because it's been projected with speed 2 meters per second. So when we're talking about it initially, we're saying that initially it has 2 meters per second. So we're going to say its kinetic energy, let's write that differently.
It also has elastic.
No, it doesn't.
Nothing, it's free.
It has initial kinetic energy. And at this point, we know it's going at 2 meters per second. It has no elastic potential energy. What does the kinetic energy get converted into? Elastic potential energy. It gets converted into its final elastic potential energy, which we'll figure out what that is in a second. Does it have any other things? Does it have kinetic energy at the end? It doesn't have any kinetic energy either. It's smooth. If it wasn't a smooth table, we would have work done against friction, but it is a smooth table, okay? So we don't need any of that kind of stuff that we've got there. So the initial kinetic energy, and it's often useful to write some of these kinds of things down that we've got. Right, let's just grab some of the information from the question to make it a bit easier. Natural length, 1.6. Modulus of elasticity, 10. Anything else? Mass is 2. We got the speed was 2. So the initial kinetic energy is a half mv squared. The final elastic potential energy will be lambda x squared, because I don't know how much the string has extended, over 2L. So a half times 2 times 2 squared, so that's 4. So it's 4 times 2 times 1.6. Let's just write that out. So we've got 4 times 2 times 1.6, which is 12.8. So 12.8 equals 10x squared. So 1.28 equals x squared. So 4 root 2 over 5. So that's how much the string extends when it gets to its point where it's stopped. So that is not what the question wants us to do. The question says, find out how far it travels before first coming to instantaneous rest. So we have to add...
To our natural length.
Good. So the distance it has travelled is L plus x, which is equal to 1.6 plus x, which is that thing we've got over there. So we get 2.73 meters to 3 significant figures. Okay? Super simple one where we've just got kinetic energy converted into elastic potential energy.
I'm just wondering, you see, when we've drawn the diagram, we've drawn that little part. Do we not include that?
What little part?
Of the string. Of the string. Because obviously...
This isn't a spring, this is a string.
It's a string.
It's a string. So I just drew it as, it's not meant to look like a springy line. I was just trying to show that there is a string that's there, and it would be like your lanyards, like just kind of like that.
Yeah.
What can you tell me?
If it was a spring,
Yeah.
I'm just thinking, because if it's compressed, if we imagine that it starts...
If it was a spring, we'd need to give a bit more like information.
Yeah.
Because that might have been the starting point.
That might have been it at resting,
Yeah.
its natural length, or it
Then
or
it's
it
all
compressed.
coming
We don't know that.
It wouldn't have tension.
We have the kinetic energy, and we will be finding x of the compression instead of...
Yeah, we'd have to consider what its initial elastic potential energy was as well. But anyway, we are going to do more complicated examples like this anyway. Can I just quickly ask you though, what is its speed after it has travelled for 0.9 meters? Yeah, why? Why is it 2?
Because it has this lost energy.
Because it's smooth, hasn't lost any energy. Okay. So that's why.
Because it's less than its natural length.
Exactly.
therefore it's
I picked 0.9, so you'd think. If I picked 1.6.
Wait, I said it, but I'm not extremely confused.
If we go 0.9, then the string is still loose because it's not reached its natural length.
Okay,
And since-
no friction, so
No friction.
All the energy just goes right on this.
All the energy is maintained until
Until this
it gets
goes
to,
beyond
until it goes beyond 1.6. When it goes beyond 1.6, it begins to slow down. When it gets to 2.73, it slows down. We know for sure this is going to come back again because it's on a smooth table. It will then hit this wall, but we don't know anything about this wall. We would need to know about its coefficient of restitution. If it wasn't a wall, then it would just go back and forth on the table, and it would be infinitely, and this is something that will come back when we do core pure and we do differential equations, and it will go back and forth, and it will follow the pattern of a sine curve, and it will be called simple harmonic motion. It will just go back and forth and back and forth. Okay? So, let's see what we've got here. A particle of mass 0.5 kilograms is attached to one end of an elastic string of natural length 2 meters, modulus of elasticity 19.6. The other end of the elastic string is attached to a point O. The particle is released from the point O. Find the greatest distance it will reach below O. So what's this scenario that we've got here, do you think? Hanging down. It's going to be something that's hanging down here. Let's just grab out some of our values. So we've got M is 0.5, L is 2, lambda is 19.6. What's 19.6 the same as in terms of G?
2G.
It's 2G. That might be useful. I often, if I see 19.6, I think it might need to be in terms of that. And we're going to find the greatest distance that it will reach below O. Okay, so the diagram that we've got, we've kind of got something that is starting. Is this right? The other end is attached to a point O. Something that's kind of starting at the top, and we know that it's going to come down to its kind of maximum point that we've got there. Okay? So at the beginning of this scenario that we've got here, what does the mass have? What energy does it have in the bank? Good. It has got, it's got its initial gravitational potential energy. And what's that getting converted to?
EP and could it be some gravitational potential energy left?
It could still have some gravitational potential energy left. However, what we will probably do is set this as the 0 line. So we can say this is where it has no gravitational potential energy. This is where it has got gravitational potential energy. And I guess we need to think about how we're going to try and describe what the gravitational potential energy that it has at the beginning and what it has at the end. So we know something about the natural length of the string. The natural length of the string is 2. So we know for sure that this distance here has got to be longer than 2.
Is the formula for gravitational potential energy MgH?
Yeah, this is just MGH, okay? It's just MGH. So we need to just figure out how are we going to describe this distance that we've got here. How do you want to describe that distance? 2 plus x. This is just 2 plus x. So the initial gravitational potential energy, m is 0.5. So it's 0.5 g times 2 plus x. This is where you've got to be really careful setting all these things out. Each little individual component gives you marks.
That the initial? The 2 plus x initial?
Because that's the distance.
Because that's the distance we know it's going to travel.
Because it includes the 2G beams.
Because look.
Oh, that's the 0.
Yeah,
That's the 0 line. We always will put the 0 line in the most convenient place. I mean, if I wanted to, I could put the 0 line 3 meters down here, but then it would mean that would also you'd have to have gravitational potential energy on the right-hand side as well. And then the final elastic potential energy is going to be lambda x squared over 2L, which is 4. And now we can spot there can be like a couple of bits of cancelling out here. Can you see any cancelling that can happen?
2 over 4 is a half.
The 2 over 4 is a half, so I can cancel the half with the 2 over 4. The g's can cancel, so I get 2 plus x equals x squared. So I get x squared minus x minus 2.
X is 2, x is 1.
X minus 2, x plus 1.
X minus 2,
Oh, you look back to
x plus 1. So either x is equal to 2 or x is equal to minus 1,
But it has to be 2 because
but the extension has to be greater than 0. So x is equal to 2. So what's the greatest distance it will reach?
4.
Great. So the greatest distance, again, is natural length plus x, which is 4 meters to one significant figure.
Well, there is a reason significant.
Do you see how in these things, it's all about naming the things really carefully to begin with, because this is obviously not hard, okay? This bit of being sensible about picking all the things to begin with, that is where the time should be spent. You know, once you've got that first line, it's easy, and you've got the question full marks if you've done it right. It's not like in other questions where you do the beginning bit and you're like, oh God, I hope it doesn't get really horrible as halfway through the question. The whole part of energy questions is the first line is where it's all at. Okay, obviously these are so simple. We've just got one thing on the left and one thing on the right. Let's do a couple more of these, okay? So, what have we got this time? Light elastic spring of natural length 1 meter and modulus elasticity 10 newtons has one end attached to a fixed point A. The particle of mass 2 kilograms is attached to the other end of the spring and is held at a point B, which is 0.8 meters vertically below A. The particle is projected vertically downwards from B with speed 2 meters per second. Find the distance it travels before first coming to rest. So what does this look like?
Compression.
So it's vertically, right? And it's being held at a compression point. And then it is just being, it's not even being released, it is being projected vertically downwards. So it's not being released, so it's also going to have kinetic energy to begin with. So we've got, this is what it's starting off like this. And we want to find out the distance before it first comes to rest. So we know it's going to come further down, like this. Okay?
So our equation thing will be
So there's 3 things to consider. Remember, you've got GPE, KE, EPE, and you just got to think about what's it got at the beginning.
EPE plus KE.
no, it has
What's it got?
Oh, yeah.
So has it got GPE at the beginning?
yeah.
Yes. Okay. So we're going to get that its initial GPE. Has it got KE at the beginning?
The point at which it's being projected, right?
Yep.
That's what we consider. Yeah.
Has it got EPE at the beginning?
Yeah, it does because compression.
It does.
Good.
When you compress a spring, you have some form of energy.
Okay. So what's it going to get converted into?
Final EPE.
Final EPE.
Sorry. Yeah, because it's going to still have stretch in the spring, so it's going to have final EPE.
And a little bit of JP still.
A little bit of GPE.
Well, unless we have our zero line there.
Well, obviously, we're going to put our zero line there. So it's only going to get converted into elastic energy. Yeah? Because it's stationary at the end, and we're going to put our zero line there.
So what's the zero line?
So where we're considering the zero waves.
Because everything has got gravitational potential energy. If you just dug a hole, it would have energy to fall into the hole. But at some point, we just need to say, like right now, I'm going to say that the floor is the gravitational potential energy. But if you zoomed out of this building, you'd be like, whoa, he's actually got loads of gravitational potential energy because he's on the second floor of a building. And if you dug a hole underneath that, blah, blah, blah. Okay, so you've got to put a zero line at all these points. Now, this is the stage where I would just be really, really careful, because if you get this first line right, you've got the whole thing that's completely correct. So the initial gravitational potential energy, well, we need to think about what it's being compressed and what we think it's going to be extending, okay? So to begin with, I should have extracted this information. We've got that the natural length is 1, modulus of elasticity is 10, and the mass is 2. And it's starting at 0.8 meters vertically below A. So this is 0.8 meters vertically below A. What sort of measurements do you think I should put on there? What's the distance? Okay, so between from here to the zero line. Yeah, it's just going to be 1 plus x. The whole thing is just 1 plus x. But it doesn't start at 1 plus x.
Oh yeah, we can say that.
So it it's 0.2 plus x. I really should have those arrows sort of meeting at the middle so it does kind of make a bit more sense, okay? So that's the height that it has above the 0 line is 0.2 plus x. So that's us dealt with this thing that we've got here for our MGH. In fact, why don't we just actually start doing that? So we've got that this one is MGH. Then we get a nice easy one. It says it's being projected downwards with speed 2. So we get a half m 2 squared. And its elastic potential energy is lambda. What's the extension or the compression?
0.2.
Lambda x squared over 2L equals the final elastic potential energy, lambda x squared over 2L. That's it, you're done. That's the question finished, right? Now you just need to make sure you're not being stupid and moving things around.
How are you using the curly one?
That's a 1, not an L.
Oh,
But how do we know x is 4.2?
How do we know x is 0.2 for the initial elastic potential energy? Because it says it's being held at 0.8, and we know that it's that, okay? So there's nothing really that can cancel here, so we're just going to have to do a bit of expanding and collecting. So we've got 2g times 0.2, so you get 3.92 plus 19.6x plus 4 plus 10 times 0.2 squared divided by 2 plus 0.2 equals 10, oh, not 10x squared, equals 5x squared. Okay?
okay.
It's another quadratic, so we get 5x squared minus 19.6x, and then we've got 3.92 plus 4 plus 0.2 minus 8.12. So we're going to put straight into our, whoops, the calculators here. Weird, bad? Have we done something wrong? No, this is good.
4.2978.
So we either get that x is 4.2978 or, yeah, would you? Or x is minus 0.377, but we know that x is greater than 0 just in the context of what this question is. So x is this one.
As long as it's not imaginary.
Yeah, as long as it's not imaginary. So distance. Now, be careful here. What's the distance that it's moved?
+1.
Nope.
That minus 0.2.
No, x plus 0.2.
Yeah, look, this is why your first diagram with the distances on it is really important. The distance it's moved was from where it started down to here, which is 0.2 plus x. So the distance moved is equal to 0.2 plus x, which is that plus 0.2. So what's that? 4.69? 4 let's just do 4.5 meters to two significant figures. Okay? I think I stole that one from the textbook. Just want to double check we got that. Yep. Do you see how this is literally what it's all about in this first line? This bit just is there's no math. This isn't maths in the way that we think of it. That bit is difficult to think about what are all of the distances that we've got here. Okay, good. We've got one on a slope now, I think. No, we don't have one on a slope. Yes, we do have one on a slope. Great. Oh, it's horizontal.
It's a rough one as well.
No, it's horizontal. I think I've got one on a slope on the next page as well. We've still got time. Okay, so we've got a spring this time. Natural length 0.5. Let's start grabbing some of the values that we've got. Natural length 0.5. Modulus of elasticity 10. Has one end attached to a point A on a rough horizontal plane. The other end is attached to a particle P of mass 0.8 kilograms. The coefficient of friction between them is 0.4. The particle initially lies on the plane with AP 0.5 meters and then projected with speed 2 meters per second away from A along the plane. So what does this look like? What kind of scenario are we talking about?
You've got a point.
Yep, Hamza's got that there.
Like that.
Yeah, it's like a table. So we've got it like this. It's like that. That's A, that's P. It's being projected away from A with speed 2. We've been, what's the distance between A and P? 0.5. Is there any compression or extension in the string, in the spring? Okay, so we know there's no elastic potential energy there, right? And we know that afterwards, it's going to go all the way along here. So that distance that it's going to move the whole way along will be 0.5 plus the extension that's in the spring. And we're now going to just think about the 3 different things that we've got, which is GPE, KE, EPE, and then we're going to think about work done against friction. Yeah, we're going to have to do some taking into account of that kind of stuff as well. Luckily, it's on a horizontal one. Otherwise, if it was on a plane, you need to find out just a few more things as well. Okay, so let's...
So we have KE initially.
We do. We've got lots of these. The only thing that we've got to begin with, because we're not going to have any gravitational potential energy in this question because it's on a flat table, so it's really just a discussion about these kinds of things. It doesn't have any elastic potential energy to begin with because it is at its natural length, okay? So the only thing we need to start with is the initial kinetic energy. That's what it's got in the bank. What's that kinetic energy going to get converted or spent on? Elastic potential energy and work done against friction. Good. So the initial kinetic energy is going to go into its final elastic potential energy plus the work done against friction. You can see I can't be bothered to write that out. Wodak frick. Okay? Let's at least do that. Work done against friction. Initial kinetic energy is easy. Final elastic potential energy is easy. We're going to need to carefully think a little bit about work done against friction. So if I were you when you were doing this in like an exam scenario, I would almost like write this first bit out, and then you can go and do some other bits of working, and then you can come back to it, okay? Because I'm doing it on the board, I might do it like over to the side of of the page maybe. So I'm going to have to work out something to do with the work done against friction. I need to work out, because they haven't told me what the frictional force is, I need to work out what the frictional force is. How do you find out what friction is?
R times
Mu r. So we know that friction is mu r, which is 0.4. What's r in this case? Good, because we know that r and mg, that should say 0.8 g there. It's a bit of a mess though. Obviously, if it was on a plane, r would not be equal to mg. You'd have to do the resolving of forces to find out what r was. So we get 0.4 times 0.8 g, which is 0.32 g. Okay, you're going to get a mark for doing that somewhere in the page as well to find out what that's equal to. So now we'll just think about what's happening in this scenario. The initial kinetic energy, what's the initial kinetic energy? Half times m times 2 squared. I think we've had the same speed in all of them. The elastic potential energy will be lambda x squared over 2L. The reason I take it slowly like this is because often this is the bit that the examiners are looking for, and then you can do some simplifying afterwards, okay? And the work done against friction. Remember, work done against friction is the frictional force times the distance that it moves against that frictional force.
0.5x plus x. No, it's just x times that.
The distance that it's moving from here to here is just x, okay? So the distance that it's moving between here and here is just x. So the work done against friction is the distance that it moves multiplied by the size of the force, which is 0.32 g, okay? So this looks like another quadratic that we've got. Left-hand side is 1.6. You can see I'm feeling super lazy today. 10x squared. And then we've got, let's just get that out of g now, 0.32 times 9.8. And then we get plus 3.136x. So you get 10x squared plus 3.136x minus 1.6. So that's 10, 3.136 minus 1.6. So we get x is equal to 0.2728, or x is equal to minus 0.586. But we know that x is bigger than 0. So the distance that it moves, do we need to add anything onto it?
No.
Nope. So distance is equal to 0.27 meters to two significant figures. Will it move after that?
No.
What do you mean?
We'll then come back.
After it rests, will it then come back again?
It'll come back because it's a spring.
Definitely?
100%.
No.
Really?
Depending on the work done against friction.
Oh, it might not come back. Imagine.
Imagine it was a really rough surface.
Oh no, it gets stuck.
What it could get stuck, couldn't it? It could go ping and then get to the end of the table, and actually it's got so much friction, it doesn't want to move back again. What would you need to find out?
In one of the errors of models.
Forces? What forces would you need to find out? Good. You would need to find out, at this value of x, you would need to find out what is the tension in the spring.
What is the friction and which one's greater?
The friction is 0.32 G. So we have to find
which
out
is
which,
greater?
we'll find out which one is greater. Should we just quickly do that as like a bonus kind of thing? So we'll be like, does it ping back? Okay, well, the tension is equal to lambda 0.27 lambda x over L, which is 0.5. So that becomes,
20 times like that. 20 times rotation.
so 0.2728 times 20. That's 5.456. The friction is 0.32 G,
Which we said was 3.16.
which is 3.136 newtons. So
It does ping back.
it does move back. So
Almost
we
doesn't.
get tension is bigger than friction, so it does move back towards A. What about after that?
Potentially you'll get stuck on the way back.
At one point, it's going to get stuck, isn't it? Because is it going to move all the way back to... It might not move all the way back to
No,
this
it
point.
won't get- I don't think it will.
I don't think it will get that far.
Because if you look at the difference between them,
Or no, it probably will get that far, but it won't get compressed 0.27.
100%.
It definitely won't. It will maybe go to 0.2 or 0.15. And at that stage, the thrust may not be bigger than the friction. If it is not bigger, then it's going to stay there. If it is bigger, then it's going to start moving back again.
Okay.
This is the kind of thing is not in the textbook. This is the kind of thing I think they'll ask you. Okay, so you need to be like thinking, what could happen here? What could happen here? What could happen here? And then keep going. Shall we do one last one, and then next lesson we'll just do all that. Do you want to try this one yourself?
Yeah.
Why don't you try this
No,
one?
I'm gonna keep going.
Should we just keep going and then we'll just do practice? And then I think this covers pretty much everything that we've got, because this is like an algebraic kind of one, and it's on a rough plane.
What do you mean mu is less than 10? What the hell is that?
It's probably a plane that's on the angle.
Well, look, mu is greater than or equal to 1 over a third tan theta. That's what we were just talking about. We were
Yeah,
saying,
it's on
is
a-
it going to move or is it not
it's
going to
on a
move?
plane.
Okay. So let's do this last one together, and then we finished further mechanics 1. And you know, we are literally doing this together. I haven't really taught you any of these things. You're telling me all the things that needs to be in here. So this is on your last page for this. Okay, we've got one end A of a light elastic string, AB, of modulus of elasticity, mg, and natural length A. I'm just going to start grabbing some of these things out. Oh, not in red, thank you very much. So we've got lambda is mg. They like using natural length as A. It's fixed on a rough plane, inclined an angle theta to the horizontal. The other end B of the string is attached to a particle of mass m. Great, m is m. which is held at rest on the plane. The string AB lies along the line of greatest slope of the plane. That just means it looks like it does in 2 dimensions, with B lower than A and AB equals A. The coefficient of friction between the particle and the plane is mu.
B lower than A.
B is lower than A. So,
It's going down the slope.
yeah, so we've got this scenario, yeah? We've got, that's the starting point A, there's the particle there, and it's like this.
Oh, okay.
So this is particle B like that. We've got that this is the angle theta.
There's no initial EP.
There's no initial EPE because,
Same as the, what do you call it?
yeah, it says
The natural length is
AB is A, so we know that that length there is A. Maybe I'll do that in a different colour so it's,
Oh, they-
so that's at its natural length to begin with.
There's friction.
We know there's going to be friction, so I want to start adding some things onto my diagram. So I know that this thing down here is mg. This thing up here is r. I can
Going
split
backwards.
my mg into these 2 bits here and here, but we'll maybe do that elsewhere on the diagram. What were you saying is going backwards?
upwards. The slope is friction.
The friction is going to be going in the upwards direction because eventually we know that there's the tension in the string will be going, we'll pull it up. It's going to be moving downwards, sorry. So the tension in the string will be moving downwards. Okay, so we're going to, again, think about the 3 different things we've got. GPE, EPE, KE. Also, work done, ag fric. Okay. What's it got to begin with?
Gravity.
0 EP.
It has got GPE, okay? It's got GPE.
Okay.
Yeah, no K.
We've got its initial GPE. It's got no elastic potential energy and it's got no kinetic energy at the beginning. So its gravitational potential energy is going to be converted into, or we haven't even read the question, show that when the particle comes to rest, okay, so that's also telling us it has moved a distance 2a brackets sine theta minus mu cos theta down the plane. So all of that initial gravitational potential energy is getting converted into
EP.
EPE because it's got a spring.
Plus WDAG. Correct.
It's getting converted into final EPE
WD silver friction.
plus WD AGFRIC, work done against friction. Okay, so we've got lots and lots and lots of things that we need to think about here, okay? I'm going to do, because this is the bit that this is the problem. I know you're going to find this bit, you won't have remembered it so well, okay? So we have got that there is something that is at this point, and we know it's going to move down to this point here, okay? We're going to name this distance that it moves, because this is the distance it's wanting us. If we call, what should we call the distance?
8 plus.
18 steps.
D? Should we call it D?
Oh, we're calling it one distance.
Yeah, we're just going to call it one distance that it moves. D, okay, we'll call it the distance that it moves. What is, because we're talking about for the initial GPE, we know initial GPE is mgh.
Because
So what is the h here? This is the height.
D sine theta.
Good. This is d sine theta. That's why in
Theta.
that's why in slope questions they always tell you what sine theta is, okay?
There's only one angle.
So our initial GPE, we can go straight in with this and we can say that it is mg d sine theta. This thing here is h. So we've got mgh for that first bit. Now when it has moved down the slope, don't know why I've changed colour, the final elastic potential energy that it's got, we would have to say, what's its extension when it's gone down d meters?
D minus A.
Good, it would be d minus a. That would be the extension that it has. Maybe this isn't the best way of doing it. No, this is good. So the final elastic potential energy is
What is
lambda d minus a squared over 2a.
But aren't we assuming that it's at the bottom of the slope now? So wouldn't it still have GP at the end?
No, because we've said that when it gets to the bottom of the bottom of the slope, that's where it's got the 0 line.
that's where the floor
Oh,
is.
okay.
I'm wondering if actually that's the best way of us doing the letters. I wonder if we should have said the distance that it moves is...
Let's keep going.
Yeah, let's keep going.
Oh, this isn't the extent. The extension isn't d minus a.
What?
Yeah, it is.
It is.
It is.
Because that's how it gets to the bottom minus the starting there.
No, because this is it here. This is me saying that's that one. So when it moves to the bottom, the extension is just
D plus A.
d.
Oh, it's just D.
It's just moved d.
Oh, I thought that's from the top. That's That's why.
This bit
Oh,
here,
okay.
this bit
That part's D.
is
Imagine
this
the
bit here.
particles at the top of the
I just drew this diagram. This bit here is it moving from here to here, okay? So the distance that it moves is not going to be that d minus a squared. It's just going to be lambda, which is mg, lambda x squared d squared over 2l, which is 2a, plus the work done against friction. The distance that it's moving, we're saying for it to go from here to here, which is from here to wherever it finishes up, is going to be the friction times by the distance that it moves. Okay, well, we need to work out what the friction is. So if we're going to try and work out what the friction is, we first of all need to find out what r is. What is r equal to?
mg cos theta.
R is mg cos theta.
Because it's that one there.
So and you get a mark for doing these bits that we've got here. So the friction is mu mg cos theta. We don't know what mu is. Everything is unknown in this question. So the work done
But
against
mu is less than tan theta, that's what it is.
the work done that we have against friction is the friction times by the distance that it's moving, and we've named the distance it's moving as that. So we get plus mu mg d cos theta. What happens? Let's clear out mg.
mgd.
MGD. Let's get rid of MGD from everything, okay? MGD. 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 Although you need to make sure that this line that you have here can still be read by the examiner, because that is probably worth, out for this bit here, this is probably worth 4 marks. Because look how much work we've done to get there. This is where mechanics is not about how much work there is on the page, it's how accurate the work is that you've got there. It's the quality, not the quantity. So we've now got sine theta equals d over 2a plus mu cos theta. What a relief.
Now we just want to.
So now we just want to get that by itself. So we'll multiply everything by 2a.
Yeah, and then little
I
factor.
didn't think that to other side and take it out again.
So you get 2 sine theta equals d plus,
2
sorry, I said 2a mu, because I don't know why I put that in a funny order. So then we get 2a sine theta minus mu 2a cos theta. I don't know why I keep putting the 2 in that place. Very, very random of me. What are we taking? 2a sine theta minus mu cos theta is equal to d. It's not hard. These questions are not hard. I know that a couple of you who haven't done physics probably are like, oh, I hate the energy questions. Just think at the beginning, what does it have? What does it get converted to? And there's always like a penny drop moment in this topic where you're like, oh, it's just simple. Okay? So it now says, given that there is no further motion. There's no further motion. So
That means that the friction must
T's
be
equals
bigger
0.
than the elastic potential.
So we need to think really carefully for part B of the question now, okay? We've got, here it is, with a piece of string. What are the forces? Okay, what would, let's imagine there was further motion. What do we think would happen? It would be pinging back, okay? So
mg sin theta equals to...
So we need to think about the forces that we've got going down, okay? So one of the forces that we've got is this one here, which is the mg sine theta.
And that's equal to mg cos theta mu.
We've got up here is the tension. Which direction would the friction be going in?
Friction is still going downwards.
It's going to be going downwards because we think it's going to ping upwards. So we've then got this way, which is mu mg cos theta. Now, we are saying, given that there is no further motion, so what do you know about this and this?
mg sin theta plus the thing
Divided by the...
Mg sine theta plus mu mg cos theta is,
tension.
it's not the tension, it is if it's not going to move.
0.
Something different got to be here.
Is greater, no, less than. No, wait. Greater than?
The downward forces need to be saying that it's bigger than,
If that's bigger than it, wouldn't it go downwards?
because this thing won't actually be that. This thing will adjust itself to make it equal to. This is, remember, this is the maximum value that the friction can take. So because this is the maximum value the friction can take, it will go slightly lower than that to make it match, okay? So we are nearly there. What do we need to do for the value of t?
Find it.
Yep.
Equal to 0.
So it's
Come on, man. You do. You want to cancel out these
lambda d. I don't know what.
Yeah.
Lambda d of L.
Lambda d.
Oh my god, I forgot we have values for all of them.
And it's all over, what's L again?
A.
Oh, yeah. All of that.
We're done.
It's
Okay, let's just, before we finish this, we're saying that because we think it's going to ping up, the only way it would ping up is if t was bigger than mg sine theta plus mu mg cos theta, which is the maximum thing that the friction can take. So if it's not going to move, then it has to be less than or equal to it. Okay? It will.
Everything other than it,
Yeah. So now we can see a lot of things are going to cancel here.
The mg.
The a cancels. The mg cancels. And I'm going to rewrite this line so it looks a lot nicer, okay? We've then got sine theta plus mu cos theta is greater than or equal to 2 sine theta minus 2 mu cos theta.
We need
Move the sign over that side.
Sine over that side.
Yep.
So you've got sine theta. That over that side, 3 mu cos theta.
Divide by 3 cos theta.
Yeah, I could have done that quicker. Mu is greater than or equal to.
Bro, in the exam, that
A third tan
thinking
theta.
about that would
Yeah,
take me
but-
10 minutes.
Yeah.
So
It's like, hey, 10 minutes, half an hour. I'll
Which
be
bit?
sitting
I'd sit there teaching myself trigonometry again just to make sure.
Okay, so let's talk about this a bit more. This sentence here is very important, okay? This is given not moving again. If it was moving again,
T is bigger than
we know if it's moving again, it's going up.
Hey.
Yeah? So if it's moving again, it's got to go up the slope. The only way that it would be moving again is if t was bigger than, it couldn't be equal to it, because if it was equal to it, it wouldn't be moving, is if t was bigger than mg sine theta plus mu mg cos theta. And the negation of this, the opposite of it being t is greater than, has to be
That.
t is less than or equal to that. Okay?
Now that you think about it, it's actually really easy.
And we're saying here, this is the friction and the weight have got to be bigger than the tension, because the friction and the weight are the thing that's going to stop it moving. Okay? And remember, this thing here is not the actual friction that it will take, it's the maximum value that the friction can possibly take. So if it was moving again, you get this statement that we've got here. Okay, we did like 5 big examples there, but we've finished all the study for this. I'll set you a few easy questions for homework, and then we'll just do loads of exam questions and stuff on Friday's lesson. Okay?
Moving on to the other pure.